Hi everybody. So I'm Vadim. I'm the head of the Autonomous Navigation Perception Lab. And in our lab, we are conducting research that is attempted to advance autonomy, obviously. And we are inspired by real-world applications, such as those that you see on this slide, where in all these applications, agents have to be able to do these advanced kind of capabilities, such as autonomously navigate to different regions both without colliding, actively gathering information, actively mapping the environment, actively sensing the environment, and understanding what is the best thing to do despite the inherent uncertainty that is out there in the world. So you can envision many, many things here, almost driving. You may ask, what is this object? Is it a car? Is it an elephant? Is it an ant? How should the agent act to be more certain about the label that we have here? Also here, what is this actually? Medical pill that you follow, right? There's some camera here, and it maps the interior of the body. And also here, when we map the environment, we have to ask different questions. How accurate is the mapping? How should the agent act to improve the accuracy and so on? Okay, so to realize these advanced capabilities, we are typically looking at least two pillars that we care about. The first one is about perceiving the environment and probabilistically inferring the state of the environment. This inference can be done in different layers, can be done in the geometric layer, can be done in the semantic layer, or both. And on top of that, we are really asking questions about decision making. How should the agent plan its own actions autonomously, given the noisy data, the noisy information we get from the first pillar? So just to be a bit more concrete, and then we'll discuss the research directions, let us discuss this very basic toy example, okay? So in this toy example, the agent is somewhere in one of the cells. This is the true location, but of course, the agent is not aware of this. And instead, the agent maintains a distribution over its state. In this case, it's just histogram, where each cell gets some probability. Okay? Now, in planning, we reason how the distribution might evolve into the future for different actions, different observations. So we can envision there's some search tree that is being constructed, and to decide what is the best action that the agent should take, we actually have to reason about all possible permutations along this tree, obviously not tractable in practice, especially when you consider high-dimensional settings, as in real-life settings, high-dimensional state, high-dimensional observations, such as images. So how can we actually do that? Okay, so our lab asks these questions, basically this question: how should the agent or a group of agents act autonomously online and efficiently perform these advanced tasks that I mentioned before in a safe and reliable fashion? So this is the basic question we ask. We investigate this question from different perspectives. I will just now mention a few of them. One of the directions is looking into developing scalable online decision-making approaches. Within this direction, we have different sub-directions. One of them is how can we utilize prior knowledge, prior experience to speed up the planning process at the current time. So imagine, for instance, we have a tree that somehow was started before, and now the agent is located in this node. This is the belief distribution, the current time plus one, but it has access to this previous tree or multiple trees. So instead of constructing a new tree from scratch, which is what is typically done these days, maybe we can somehow utilize this past information in a statistically meaningful way to speed up the calculations such that the online decision making becomes more scalable online. Another direction under this setting is what we call simplification, meaning the concept is the following: let us take the original problem that's quite difficult to solve and identify some simplified version of that problem. For instance, we might want to sparsify matrices. We might want to account for only a subspace of the state space, action space, observation space, but not the entire spaces that we cannot do in practice. If we do that, so we kind of solve simplified variants of the problem. And what is interesting for us here is how can we formally provide guarantees that although we solve that simplified problem, what kind of guarantees can we provide for the performance of the agent will have. So we have quite a few things that are going on in this direction. Another direction it deals with inference and planning with hybrid beliefs. These are beliefs distributions over discrete and continuous random variables. There are different motivations for this direction. I'll mention two. One, in the first motivation, we are looking into semantic perception, meaning the ability to understand the environment, that this is a chair, this is a car, and so on. And it turns out that the semantics, the fire, deep learning, not deep learning, doesn't really matter in this case, actually is viewpoint dependent, meaning if you observe the scene from different viewpoints, the output of specifier will change, obviously. And so we have this notion of viewpoint-dependent semantic models that basically couple between semantics and geometry. Because of that, we have to maintain those hybrid beliefs as continuous variables and discrete variables, which are the last space. Another reason for these hybrid beliefs is that we have, let's say, ambiguous settings. We're not sure, are we looking at the left bicycle or the right bicycle? So we have here two hypotheses, basically, to the left or right. And you can envision as we go on with time, the number of hypotheses will increase very rapidly, exponentially actually. So after some time, we'll not be able to support all the hypotheses because it's exponential. So we have to reduce the number of hypotheses. This is the simplification that I talked about. And then the question is, how can we do inference? How can we do planning with those other beliefs? And what does it mean? What is the impact of us tuning away those hypotheses? Maybe I will tune something variable that is important. What is the impact on decision making? What kind of guarantees can we provide? Another interesting topic, in my opinion, is this one, is the multi-agent COMPT setting, where we have a bunch of agents that have to be act together, either in the cooperative setting or a non-cooperative setting. And what is unique in this direction is that we account explicitly for environments where the agents cannot fully share information with each other. So they have some limited data sharing capabilities for some reason. And because of these limited data sharing capabilities, the agents maintain different beliefs about the environment. Right? Because each agent has its own data now, because the data was not fully shared with each other. And because of that, these bad things can happen. For instance, if this agent does not share with the other agent its own observation, or limited data sharing capabilities, then instead of synchronizing and identify the best actions, not to follow this dangerous area and reach the goal, instead of that, each agent has its own belief, and they might collide eventually, or more generally, have inconsistent or suboptimal performance, which clearly we want to avoid. So in this direction, we address this challenge of how can we guarantee some consistency in their collaborative, decentralized decision-making, despite having these limited data sharing capabilities. And one of the students, Moshe, has a poster here. We can talk with him later if you want about this direction. Finally, I want to mention one more major direction in the lab. This is a more recent direction. We are looking into robust risk-aware constraint COMPT planning settings. We would like to develop robust methods, robustness to uncertainty in the models. We all know that models are learned these days. They are not necessarily accurate. The real model is different than the one that we are working with in the simulator. And yet we are doing planning using the data from the simulator mainly. How can we be robust to these type of uncertainty in the models? How can we be risk aware? The distribution over the return or the reward is actually might have a long tail, might be multimodal distribution. How can we talk about the risk of having a catastrophic event and so on? And finally, this goes to both the things go to how can we develop safe autonomous decision-making capabilities in an online partially observable set. Okay, thank you.